Hello, welcome to this lesson in engineering circuit analysis. This title of this lesson is called Important Three-Phase Circuit Terminology. Now I promise this is the very last lesson of background material before we jump into solving our problems. But if I just take a few minutes discussing a little bit of terminology, then when we solve our problems, it'll become much easier to explain what to do. If I start talking about the phase current, the phase voltage, and the line current, and the line voltage, you have to have a real clear understanding in your mind what that stuff is. So in order to do that, I've got a couple of diagrams on the board. Now this is a general Y-connected load. You can see you have three phases, A, B, and C, and you have three loads, A, B, and C, right? So that's not surprising, and you can kind of turn your head sideways and convince yourself that this is a Y-connected load. We're going to talk about this one first, but I also drew what a delta-connected load would look like. So again, from the outside looking toward the load, you still have the same A, B, and C terminals. You still have three terminals, but instead of being connected in a Y fashion with a common neutral central conductor there where everything comes together, you have it in a triangle shape, and that's why it's called a delta connected load, because it's a little triangle shape here. Each phase of the load has a load impedance. We just call it Z delta. They're all the same. Everything has to be balanced. So if it's 2 plus J3 ohms of impedance, then this has to be 2 plus J3, and this would also have to be 2 plus J3, just for example. And then we have some currents and things I'll talk to you about a little bit later. But basically you have the three terminals, you have VAB right here, and then this is what a delta load would be look like. Now in practice, what we're going to actually do is start solving the Y-connected load problems first. All right, so we'll have a Y-oriented source connected to a Y-oriented load, connected with the three phases, of course, and we'll learn how to solve those problems. But the roadmap going forward is that the loads don't have to be Y-connected. They can be delta-connected like this. And they're slightly different equations, a little different flavor of equations. They're all similar, but they're very slightly different in how you handle that case. And then, of course, the generators on the source side can be Y or delta also, and we'll get to that when we get there. But for now, I'm just talking about terminology. The goal here isn't to show you how to solve this problem. The goal is to tell you the terminology. So the first thing I want to do is go back to what we're familiar with. This is the Y-connected load, and I want to write down a couple of very important definitions, and I'm going to compare and contrast how they're different when you talk about Y loads and delta loads, because as we solve our problems, we're going to throw around these terms all the time. Now the first thing we need to do is just reorient ourselves. We have a neutral conductor, which is the center where all of the three loads are connected at the common point. We call that the neutral, right? And over here we have the A, B, and C terminals that are connected to the line. So if you look this direction, you have the three lines, and then you have eventually a source over there. We haven't drawn that. This is just the load. Now we've labeled two voltages. The first voltage is VAN, that's the voltage between terminal A and the neutral terminal. We called that the line to neutral voltage. We're going to write this down in a second. And then we also said, hey, we have the line to line voltage, VAB. Now I didn't draw all of the polarities and the labeling for all the other phases, but you need to know in your head that there's also a VBN, which is a line to neutral voltage, and a VCN, which is another line to neutral voltage for the other two phases. And likewise, just like we have VAB, which is line to line, we also have VBC, which is line to line, and we have VC, it goes backwards, VCA, to get back up to the other line to line. So all of the line to neutral voltages are there, and all of the line to line voltages are there. And we also have, I only drew one of them again, the current going through the line, lowercase uppercase a. Remember, we cut it here, but this direction there's a lowercase a, so that that kind of implies the current going from lowercase to uppercase a. That's the current in this phase. But again, you have to keep in your mind there's also a B phase current, IBB, and a C phase current, ICC. So everything's there. I'm just not trying to clutter up the drawing when I explain the terminology, right? Everything is there though. And we learned in the last couple of sections, basically we spent a lot of time learning how to convert between this voltage and this voltage. The line to neutral voltage going to the line voltage. We spent a lot of time. Now we finally want to do some definitions. We need to talk about a few things. When you see phase voltage, all right, what do we mean? Now also, I want to kind of point out here in the beginning, when I talk about phase voltage, line voltage, and all that, I'm talking about this drawing right here. Forget about delta loads for a minute. I want you to think about it in terms of Y-connected loads, and then we'll expand it into